Hello everyone. This is a supplementary YouTube lecture for chapter 31. In the class we couldn't finish the chapter 31, so I'll finish the chapter 31. We have covered the Euler's formula by using the Taylor expansion, and this is the actual the Taylor expansion of the sine part, and this is the sine function. So the blue graph is the perfect sine function as a function of theta, and these are the y1 is the green curve straight line. Y1 is the first part of the Taylor expansion, which is theta, and y3 is this curve here, which includes three components: theta minus theta cubed over 3 factorial and theta to the 5 power over 5 factorial and so on. So this y2 is the red curve, which is like this. So as the number of Taylor expansion components are increased, it becomes closer and closer to the real y equals sine theta function. Right. And this is the cosine function. If we have a second up to second term, this is the y1, it is represented by a green curve, and y2 includes the three components, y4 includes 5 components, and this is real cosine function. So as the number of the components in the Taylor expansion increases, it becomes closer and closer to the real function of cosine theta. So we have the y1, y2, it has the 3 components, y3 has 4 components, so y3 has 4 components, y5 has 5 components, and so on. So that's the proof of the Euler formula, and the reason why I use Euler formula is because this kind of the cosine, let's say the addition of cosine function, if I add theta 1 plus theta 2, then the real part of this one becomes cosine theta 1 plus theta 2, and the imaginary part becomes sine theta 1 plus sine theta 2. And if we have two components of the Euler form separately, then we have cosine theta 1 plus I sine theta 1 and so on. Then if we have a product, that this is the real part and imaginary part. So this is the real part and imaginary part. So the cosine theta 1 plus theta 2 should correspond to this real part, and sine theta 1 plus theta 2 should correspond to this one. So we can easily prove that cosine theta 1 plus theta 2 is cosine theta 1, cosine theta 2 minus sine theta 1 and sine theta 2. And sine theta 1 plus theta 2 becomes like this. So the addition of the cosine and sine terms appears as the product in the Euler formula. So this is the reason why we frequently should use Euler form instead of the sine and cosine functions. And same is true for the derivative of this. If we have exponential I sine theta, and if we take the derivative with respect to theta, then we can easily obtain I exponential I theta. which is the I cosine theta plus I sine theta, because this one Euler expansion is this one. So we can easily prove that cosine function derivative becomes minus sine theta, and the derivative of sine function becomes cosine function based on these properties obtained from the Euler formula. So there are a lot of reasons why we should use Euler formula, and a lot of communication theory and the wave theory, as well as in quantum mechanics, all functions are represented in the Euler form, and all observable quantities in physics should have real functions. So after we calculated or represented a function in an Euler form, if we like to have something that has a physical meaning, then we just can take the real part of that function. That's the trick we use in quantum mechanics, and a lot of the oscillation or wave functions, we use just the Euler form instead of sine and cosine form. So as you know, that if we have the x and y in the complex plane, then we represent that in a polar coordinate, where we represent the point with the radius and theta in the 2D polar coordinate, where the relation between r and theta with respect to x and y has this relation. R becomes x square root of x squared plus y squared, and theta becomes arctangent of y over x. That's the basic relation between the x and y and r and theta coordinate. So in the complex plane Z, we represent the real part of Z as x and imaginary part of Z as y to represent the complex function Z in the xy plane. And here we also represent the Z with r times exponential I theta in the polar coordinate form. Then we have the x equal r times cosine theta and y equal r times sine theta. Right. And here we define impedance, which is Z, and which is just the ratio between the voltage divided with the current. So voltage becomes Z plus I, where Z is called the impedance. If there is just a resistor, the impedance of resistor is just R, real value. Impedance of resistor becomes R. Here, as impedance of a resistor is the real value, the voltage and the current does not have any phase lag. So they have the same phase because R is a real number. And if there is a capacitor within circuit, then then we represent V, the source of the voltage, as V0 exponential I omega t. The real voltage is the real part of the complex function of the voltage. So if we take the real part of this one, this becomes the V0 cosine omega t. And with a simple relation between voltage and the charge, we have this relation. And if we take the derivative of this equation on both sides, then we have dV over dt. That's the derivative of the voltage across a capacitor becomes derivative of charge is I, so it becomes I. So as the voltage is given as the V0 exponential I omega t, where the voltage given by the source is equal to voltage at the capacitor. So this is from the Kirchhoff's law. So from this relation we can take the derivative of Vc over dt, dVc over dt, with this dVs over dt. Vs is given as V0 exponential I omega t. So this one becomes I omega times V0 exponential I omega t. If I multiply that with C, then we obtain IC. IC becomes C times derivative of the voltage with respect to time, which is I omega times V0 exponential I omega t. So we obtained IC as the I omega c V0 exponential I omega t, where we can replace I with exponential I pi over 2 or 90 degrees. So we can also represent this like this. And if we take the real part, which is the real part of the complex notation of the current, then we have the cosine instead of exponential I function. So if we take the Vc over Ic, Vc is given as Vs, which is V0 I omega t, and Ic is I omega c V0 I omega t. Then V0 I omega t cancels out, and V0 cancels out, and we have only 1 over I omega c left. So impedance of a capacitor, which is the ratio the voltage of the capacitor divided by the current of the capacitor, becomes 1 over I omega c. So we just define or memorize Zc, which is like the resistance corresponding to a capacitor, becomes 1 over I omega c, which is the complex number. Similarly, if we have just an inductor here, voltage is given as a complex number like this, V0 exponential I omega t, and as there is only one component, Vc should be equal, Vs should be equal to the Vl because of the Kirchhoff, the circuit law. So, and the Vl is given as L di over dt. That's the Faraday's law representation by using the inductance L. So as Vt is given as, so Vl is given as Vs, Vs given as V0 exponential I omega t. So we have the di over dt becomes V0 exponential I omega t over L. Right. So right. What was that? Let's say. therefore, we can, by taking the integral of both sides, then we have IL on the left side, and integral of this one becomes V0 exponential I omega t divided with I omega. L was already here, so exponential, if we take the integral of this one with respect to t, we should divide this with I omega here. So I t IL as a function of time should become should be like this. So we have this representation, and the relation between the VL and IL, if I take the VL with this function V0 exponential I omega t, IL as this function, then we have the I omega L for the ZL. So these are the three parameters we have. For a resistor, we have ZR equal R. For a capacitor, we have ZC is 1 over I omega C. For a inductor, we have ZL equal I omega L, where each of these impedance is used to calculate the voltage, the relation between the voltage and impedance. So as ZR is the real number, there is no phase difference between VT and IT. As this is the complex number, there is a phase difference between VT and IT. Same is true for the ZL. ZL is a complex number, so this is a magnitude of this one is 1 over omega c, and this is 1 over I with this exponential minus pi over 2, where this is the phase term is I, so I corresponds to exponential I pi over 2. Here exponential minus pi over 2. So these are the phase term related to a capacitor and inductor. So let's say by defining this, we can easily calculate many complicated circuits like this. If we have a resistor and inductor connected in series, then the impedance is just if we have two resistors connected in series, then total resistance is Z1 plus Z2. If we have Z1 here, one resistor here, another resistor Z2, R2, then total resistance is just R1 plus R2. Similarly, if we have one component ZR and one component ZL, total impedance is just a ZR plus ZL. Here ZR is the impedance for a resistor, ZL is impedance for an inductor. As they are connected in series, we just add two impedances together. Then the ZR is R, ZL is I omega L here. ZL is I omega L. So we just add those things together, and we represent this in a polar coordinate. So the magnitude is rho and phase is phi. Here the magnitude is the R square, real part square, and omega square L square. That's the imaginary part, amplitude imaginary part. The phi is tangent, arctangent of the real part, the imaginary part over real part, omega L over R. So that's the phase. As the voltage is given V0 I omega t here, this is given, and we can consider this is one element whose Z effective is given with this rho exponential I phi. So as Vs is given with V0 exponential I omega t, and Z effective is given with this number. If I divide voltage with Z effective, we have rho V0 of rho exponential I omega t minus V, because this is here is exponential IP, but we should divide that, so we have minus V. So rho is given like this, so we can just replace rho, and phi is arc tangent omega L of L R. So without calculating this, by using simple definition of ZR, ZC, and ZL, we can just add those things together to calculate the phase difference between the current and the voltage here when the R and L is connected in series. Similarly, we can once we calculate the current, we can calculate the voltage across a first element ZR and ZL independently. The voltage across a resistor is VR. For a given current is same, so for a given current, voltage is just ZR times the current. So we have just calculate this. Then voltage across a resistor is just ZR times IT. V equals IR. So we have the impedance of resistor here times the current. This is the one we have just calculated in the previous page. So as we just calculate this, we just multiply with R to obtain the VR. So we just multiply R with the IT here. V0 over rho exponential I omega t minus phi. That's the IT here. IT is replaced with this number, this expression, then we have R times V0 over rho exponential I omega t minus phi. That's the voltage across the resistor. The voltage across the inductor, we can calculate the VL is L di over dt. So as we already calculate I, we can take a derivative of this one. Then if we take a derivative of this with respect to time, then we have just I omega term appears at the amplitude part. So we have I omega here and the same expression, the IT. So that's the I omega, and L is put over this at this point. So as we have another I, we can express this with the exponential I pi over 2 or exponential I 90 degrees. That's the that's the extra phase term appears in the voltage function at the inductor as a function of time. The real voltage over here is, as I mentioned, the real voltage here is just the real part of the expression, complex expression over here. So only thing you have to do is exponential part is replaced with cosine term. So that's the real the voltage, of course. Same is true for the current. Current is a measurable quantity. Same is true for the voltage. Voltage is a measurable quantity. So measurable quantity should be always a real function. So even though we calculate all the the complicated functions with the complex notation. At the end, when we have to express the measurable quantity, we just take the real part of the function we used in the Euler form. That's the trick we have. Example 2 is when there is a resistor and capacitor. Same thing happens. We can consider this as a single element as they are connected in series. We just add these two, ZR plus ZC as the effective Z as a single element. And ZC is 1 over I omega C. We just add these things and we define that as a rho exponential IT. Here rho is the square root of R square plus 1 over omega square and C square. This is the imaginary part and real part, so we have the rho given like this. The phase defined here is the tangent, arctangent. The real part R, the imaginary part is omega 1 over omega C, divided with the real part is omega RC. We take the minus sign because there is a 1 over minus 1 over I becomes minus I, so we just take the minus sign out because 1 over I becomes I, so I just took the minus sign here. So here again we can calculate the current passing through this circuit by assuming these two components as one component. It has the complex impedance Z effective, which is this one. So that once we calculate this, we can also calculate the voltage across the ZR and ZC, where the voltage across the resistor is R times I, the expression given here. The voltage across C is the what's that? This voltage across the ZC is just the ZC times the current. So this times current, we can calculate the voltage across the capacitor. Same is true. We can calculate by this definition, but voltage across the inductor is I times the current times impedance of the inductor. Impedance of inductor is I omega L. So instead of taking a derivative, we can just multiply impedance of the ZL, that is I omega L. So we can just multiply I omega L with the voltage. This is the current. So this is the current. So if we multiply I omega L with is ZL, ZL is I omega L here. If we just multiply that ZL, this is up to this part is the ZL. If we multiply this with the current, which is given as this, then we obtain the same result. So I think I should have written this instead of this. I just should represent this as ZL times I. ZL, it is I omega L times the I. So that's sequence you should follow to calculate VL. Here, as we calculate IC, the voltage across the resistor is just I times R. Voltage across the capacitor is I times the impedance of a capacitor is 1 over I omega C. So voltage across this capacitor is 1 over I omega C times this current. That's the voltage across the VC. So we can calculate that as well. What if the resistor and inductor are connected in parallel? We can consider that as one element, and if two resistors are connected in parallel, then this is the total resistance becomes 1 over R1 plus 1 over R2. Same thing, same equation can be applied for the impedance. If the total impedance is Z effective, then 1 over Z effective should be 1 over ZR plus 1 over ZL. The ZR is R, so we have R here. ZL is the I omega L, so we have I omega L here. So this addition of this one is defined rho exponential I phi, where the Z, that is 1 over Z effective, so right. So we have the rho given as this and the phi given as this, as we have the I in the 1 over I, so we can take minus sign out, so we have this phi. And as we know, as we calculate 1 over Z effective, the current should be V over Z effective, so we just multiply this with the voltage. So if voltage given, source voltage is V0 exponential I omega t, just source voltage times 1 over Z effective, that is rho times exponential I phi, then this becomes like this. So this is the current passing through this circuit. So we don't know what is the current passing through this component and this component, because current coming into these two components connected in parallel is the total current IT. This is the total current passing through this whole circuit. So we don't know yet what is I passing through the resistor, what is I passing through the inductor yet. But we can, as we know the voltage across it is same as voltage across the resistor, this component should be equal to this component, and that is V0 Vs. So as we know the voltage and impedance, we know the current, we can calculate current. Current is V divided by the impedance of resistor, and current through this one is V divided with the impedance of this one. As the impedance of the inductor is I omega L, so the current passing through this component is this divided by I omega L. Current passing through this component is the voltage divided by R, so we can calculate the current passing through each component independently. Same thing happens for a situation where the resistor and the capacitor is connected in parallel. Then we can consider this as one object, one component, and as they are connected in parallel, so total impedance Z effective, 1 over Z effective should be 1 over ZR plus 1 over ZC. where the ZR is R, ZC is 1 over I omega C, so 1 over ZC becomes I omega C here. So that is defined like this. Then we can also calculate the current for a given source voltage with this expression, and this is the expression. So what if we have 3 components connected? Then we just add those things, and there is 2 imaginary part here. If I take I out, omega L minus 1 over omega C comes out here. We define this as rho exponential IV. Then the current passing through these 3 components are same, and that current can be calculated with this simple expression where the voltage is given as V0 cos exponential I omega t, and the rho is given like this, P is given like this. Calculate things. And there is a phase diagram, and there is one thing which is sometimes very important. If the situation, this is the energy conservation for transformers. If there is n1 number of turns for this voltage V1, and if there are n2 number of turns for voltage V2 as an output, then the V1 times I1 is the power through this circuit, and V2 times I2 is the power through this circuit as well. From the Faraday's law, we have V1 divided with N1 is equal to V1 divided with N2. So V1 can be represented as N1 over N2 V2. So if N2 is 20 and N1 plus N2 is 4 and N1 is 2, so N1 is 2 and this is 4, then V1 is 1 over 2 V2. So if V2 is the output, this if N1 is 2 and N2 is 4 as illustrated here, then V1 is 1 over 2 V2. So if we have originally 100 volt, then we'll have, this is 100 volt, then V2 becomes 200 volt because N1 is 2 and N2 is 4. So we should have 200 volt as the output. So as we have twice as many number of turns for the second coil compared to the initial coil, we have twice of the voltage at the secondary coil. So that's the voltage of the transformer. Then because of the energy conservation, the current ratio between the coil 1 and coil 2 will be I1 is twice as much as the current current passing through the coil 2. If this is 200 volt and 100 volt, if this is 2 and 4, then the current over here is half of the current passing through the coil 1, because this is 2 to 1, so I2 is twice of the I2. I1 is twice of the I2. So that's the relation So if there is a resistor at the secondary coil, that is V2 over I1, because the Ohm's law V is equal to IR. So R2 is the V2 over I2, and the R1 is the R1 is let's say if there is a R1 connected to the first circuit, then the right. If this resistor can be considered as R1 in the primary coil, such that even though there is a resistor at the secondary coil, we can consider as if it is directly connected to the first coil, which provide the same amount of power, which is V2 over I2. If we make then if R1 is defined as V1 over I1, where the V1 is given like this, I1 is given like this, with the relation between V2 and I2, then we have this. So this one becomes this one is I1 N1 over N2 square times V2 divided with I2, but V2 divided by I2 is defined as R2, so we just replace V2 divided by I2 with R2. So right, so right, so that's the relation. If N1 is 2 and N2 is 4, this is 1 over 2, square of this one is 1 over 4, so R1 is equal to R2 divided by 4. Right. So if we have this relation, even though there is a R here, it has this equivalent effect as R1, which is 1 over the R2 over 4. That's the effect of having R at the secondary coil. Even right, that's the relation. So this is one of the reasons why people use a transformer to a long distance transmission line. So people like to right, that's the reason why people use transformers actually to transmit the long distance power to the long distance consumer. Right. That's about it. So I'll finish the chapter 31 at this point.